First thing to consider during the initial design cycle phase is the required bands of operation. Attention to the bands of operation covered by the radio module must be considered in order to understand the frequency requirements of the antenna, which will dictate the minimum size of the PCB and the overall device size. Carrier bands of operation, radiation limits, and geographic regions will dictate device size as well. In the US, the carriers have bands that go down to 600 megahertz, requiring ground plane lengths of greater than 130 millimeters for the device to work properly. Antenna physics by nature will dictate the size necessary for proper operation. Sacrifice in performance for device size will limit your antenna type, such as your flexible printed circuits versus surface mounts versus trace antennas. Smaller device ground planes will hamper the use of lower frequencies on board antennas and dictate the use of higher frequency bands while limiting the coverage of those lower frequency bands for certain types of antennas. So the higher frequency that you have to cover will allow for smaller devices, such as Bluetooth and Wi-Fi, that will allow for smaller board sizes because they're higher frequencies. So project planning practices ahead of product development tend to speed up time to market and reduce the back-end redesign. So let's talk about the different types of antennas you can integrate into your product. Antenova has had great success with surface mount designed antennas integrating into many different device platforms. The great thing about the surface mount antennas is you can use the pick and place system in order to populate these antennas onto your printed circuit board. That tends to speed up the manufacturing process and lower your manpower costs. Another great thing about it is that they're lower profile, so you can fit these in devices that are fairly slim. They are ground plane reliant, so in order to have a balanced system, you do need to have the proper ground plane length, like I mentioned before. For the lower frequencies, you do need to have a longer PCB in order for the antenna to perform at its optimum. The smaller the ground plane gets, you do sacrifice performance. The next antenna type I'd like to go over is the blade antenna. Blade antenna is used to shorten the overall device length when your device needs to be small, such as like the OBD or onboard diagnostic devices. These blade style antennas require the interaction of a pogo pin or something to contact between your main PCB and some pad landing points on the blade style antenna. Those can be added to your design by using pogo pins, or if you need something a little more robust, you can solder header pins to through-hole vias on your board and then to the antenna, or use a C-clip soldered to the main board and touching on landing pads on the antenna itself. Flexible printed circuits, or FPC antennas, are copper traces that are printed on a mylar tape. This tape can be used to stick the antenna on the inside of your chassis and allow the antenna to get away from the printed circuit board. That way they operate more efficiently. This allows for your printed circuit board to be significantly smaller. However, in order to achieve the lower frequencies, you still have to have a longer antenna, which tends to make the FPCs a little bit longer. So it's kind of a trade-off. With the FPC type antennas, you feed them through a coaxial cable that attaches to your radio via a U.FL or IPEX connector. And by using the flexible printed circuits, you can make them smaller, but what happens is the currents tend to run down the coax, and therefore the coax becomes part of the antenna or the counterpoise. In doing so, you have to be very careful of how you route that coax cable, because if it comes close to ground or comes close to some noisy components on your printed circuit board, you'll find that it'll act as an antenna picking up the noise from your board instead of operating as the antenna for your radio. And that noise feeding into your receiver front end will degrade your overall radio performance. These antennas also tend to be a little hands-on when you're manufacturing with them. In saying that, what I mean is that somebody has to stick it to either a carrier or the inside of your device. So that in itself takes time, and it also allows for some irrepeatability or some difficulties in repetitiously placing the antennas in your device. One thing you can do to overcome that is to put pins inside your housing or on a carrier so that those pins align with holes on your flexible printed circuit antenna, and you can have a little bit of repeatability. The last antenna I'd like to cover are the terminal type antennas. These mount to the outside of your device and typically have the best performance. They attach via SMA connectors that stick out of your chassis, or they have cables that will run inside your chassis and allow for connection via a UDOT-FL or IPEX connector. These antennas are used in critical communication systems such as medical devices or fire, anything that's mission critical. So the efficiency on these antennas tend to be a lot better because you can get them away from your device, the ground plane, or any other metal parts of your device that tend to cause issues with the antenna performance. They are also not ground plane reliant because they have a balanced antenna structure inside of them, and therefore you can mount them pretty much anywhere on your device without having them be detuned by a smaller ground plane. The last thing to consider during your design cycle are the main challenges of wireless design. Consideration for the antenna placement should be the first priority and the top priority. Placement of the antenna inside the device should not be near metallic objects such as Ethernet connectors, USB-C connectors, battery supply lines, data lines, LEDs, or the LCD of your device. All of these generate noise, and the antenna can and more than likely will pick up that noise over the signal that's the desired signal that you're trying to receive. Follow the antenna vendor's guidelines from the outset of the project. Once you determine the type of antenna you will use, follow the guidelines listed in the manufacturer's data sheets for ground clearance and ground length required. Antenna placement is also something to consider. The printed circuit boards can get pretty densely populated, so the certain antennas can function better along the long edge of the PCB. Others will like to take up the end of the short length of your PCB, and others function fairly well near the corner of your device. So the antenna position is critical, but can be manipulated. Be sure to clear all metal objects, including, on some of the surface mount antennas, the copper that is running through the board layers. Some antennas need to have that areas cleared out. We call that a keep out, and allows for the antenna to operate properly when it's mounted to the surface of your printed circuit board. Other things to consider are not to run power supply lines or data lines underneath the antenna, as this will cause the antenna to be detuned and you have a loss of energy, radiated energy, and also could possibly pick up noise from whatever circuit is supplying those traces. So be sure to consider this as priority, not running parallel lines to your RF feed trace or running data lines underneath your antenna.